In this video, we will explore data warehouses and data lakes, both of which are important for storing and processing large-scale data. We will also learn about OLAP systems. Let's start with the data warehouse. A data warehouse is a centralized repository of integrated data from multiple sources. This data is optimized for analytical processing and business intelligence. In simple words, it collects data from different sources and keeps it in one place so that you can easily analyze it to make better business decisions. Here's a typical data warehouse architecture. At the beginning, you have data sources which include online transaction processing systems, simple files, and external application programming interfaces. The data from these sources is then passed through an extract, transform, load layer or ETL. In this layer, data is extracted from various sources, transformed into a consistent format, and loaded into the data warehouse. The data warehouse stores this data in an organized way using schemas such as the star schema which you see at the center. Lastly, the presentation layer includes online analytical processing cubes, reports, and dashboards that enable users to analyze the data and gain insights. In the code example, it shows a simple illustration of an extract, transform, and load pipeline written in Python. Now let's understand the concept of a data lake. A data lake is a scalable storage repository that holds vast amounts of raw data in its native format until it is needed for analysis. Think of it as a large lake where you dump all your data without structuring it first. This allows you to store structured, semi-structured, and unstructured data. Let's compare data warehouses and data lakes. In a data warehouse, the structure is schema on right, meaning you define the structure of the data before you store it. It mainly handles structured data. It follows the extract, transform, load process before storage. This usually leads to higher storage costs, but it provides fast query execution. The main use case for data warehouses is business intelligence, where quick and reliable insights are needed. In contrast, a data lake uses a schema on read approach, so you define the structure when you read the data. It can store all data formats, whether structured, semi-structured, or unstructured. The extract, load, and transform process happens after storage. This leads to lower storage costs, but the performance varies based on the processing. Data lakes are commonly used for data science and machine learning, where flexibility and variety of data are crucial. Now let's explore online analytical processing, also known as OLAP systems. The purpose of online analytical processing is multidimensional analysis of business data to support decision-making through complex analytical queries and reporting. In other words, OLAP systems help you analyze your business data from different angles to make informed decisions. OLAP systems include operations like slice, which selects a specific subset of data, dice, which extracts a portion of a data cube, drill down, which navigates to more detailed data, roll up, which aggregates data to a higher level, and pivot, which rotates data dimensions. One of the most common designs for data warehouses is the star schema. A star schema consists of one or more fact tables referencing any number of dimension tables. The fact table contains the measurements and metrics, while the dimension tables contain descriptive attributes related to the facts. In this diagram, you have the sales fact table at the center, surrounded by dimension tables such as product, customer, time, and location. Each dimension table provides additional details about the sales facts, allowing for more detailed analysis. For large-scale data storage, there are various technologies available. Distributed storage solutions include the Hadoop Distributed File System, also known as HDFS, Amazon Simple Storage Service, also known as S3, Google Cloud Storage, and Azure Blob. For data formats, common choices include Parquet, which is a columnar storage format, Optimized Row Columnar, also known as ORC, Avro, which is a row-based serialization format, and Delta Lake, which provides ACID transactions. The code example shows Parquet file operations using Pandas library in Python. When processing large amounts of data, there are two main patterns to consider. Batch processing and stream processing. Batch processing involves processing large volumes of data at scheduled intervals. It has high latency, often hours or days, but very high throughput. Batch processing is commonly used for ETL jobs and generating reports. Tools like Apache Spark and Hadoop are well suited for this pattern. Stream processing involves processing data continuously as it arrives in real time. It has low latency, often milliseconds, but moderate throughput. Stream processing is ideal for real-time analytics. Apache Kafka and Flink are popular tools for stream processing. A modern data architecture typically combines elements of both data lakes and data warehouses to handle diverse data processing needs. It starts with various data sources such as applications, Internet of Things devices, and logs. This data is ingested into a data lake, where it is stored in its raw format. From the data lake, the data is processed using tools like Spark, Kafka, and Airflow. The processed data is then loaded into a data warehouse, where it is curated and optimized for analysis. Finally, the data in the warehouse is used for various analytics purposes, such as business intelligence tools, machine learning models, and reports. Key benefits of this architecture include the ability to handle both structured and unstructured data, scalable processing capabilities, real-time and batch processing, and cost-effective storage solutions. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.